What are some common moments of inertia? So let's see, right off the top of my head, uh, the sphere, maybe my favorite one. I don't know. You say, why is it your favorite? Well, it's maybe the simplest object. All it has is a radius, right? And the moment of inertia formula for that is 2/5 mass of the sphere times the radius of the sphere squared. So many of the moment of inertia formulas are some number multiplied by a mass times some length squared. If it's a radius, it's probably going to be an r, but we'll see there are some other ones, right? So another example might be a cylinder. This could also apply to maybe a disk, because really the difference between a cylinder and a disk, like if you take a cylinder and you say, okay, let's shorten its length, now you have a disk, right? So anyways, but I'm just going to say cylinder, and I'm imagining the axis of rotation going through the length of the cylinder, which would kind of mean that it's, I guess, if it were a disk, how do you describe that in words? It would be going right through the center of the disk, the axis of rotation, right? I mean, the way it would, maybe you imagine a disk spinning, right? What's the natural way that it spins? That's the rotation axis. Other ones doesn't look quite as symmetric. Not that there aren't possible moment of inertia expressions for those. I just don't know what it is. I'd have to go and figure it out. And there are some techniques out there for doing that, although a simple one is to go to Google and type some search in, right? See what comes up. You can find some pretty exotic ones. Let's see. Another one might be, there's a couple formulas for rods that I usually remember. But it depends on what your rotation axis. So I'm going to say rod center axis. In other words, the axis is kind of through the center of the rod. So the rod is kind of going around like a propeller, in a sense, is the rotation I might be imagining describing. And that one, the formula is 1/12 m L squared, where L is the length of the rod. But there is also a formula for the rod if it's kind of spinning around one end. So maybe I'll just say here end axis. I don't know if that makes sense. I'm kind of just doing this on the fly here. But that one is 1/3 m L squared. So that's 4 common ones already. You know, another one that does come up sometimes might be a hollow cylinder. And this one's kind of interesting. Because like if you have a hollow cylinder, what do you need to describe a hollow cylinder? So I'm talking about like, you know, if the cylinder, if this is like maybe the outer edge of the cylinder, but then it's hollowed out, right? So there's a hollow section. Maybe it's kind of like a pipe, right? With a hollow interior. So there'd have to be two kind of radii, right? There'd have to be the radius of the outside and the radius of that inside hollow part. And maybe I could describe that with like a B and an A. And I think for that one, let's see if I get it right. My memory's getting a little hazy on this one, but I thought it was 1/2 m times A squared plus B squared. And I know in the past I've had some discussions, or I've had questions come my way. How does this plus really make sense, right? I mean, if the hollow, if you just remove that part, shouldn't it maybe be like B squared minus A squared? But it turns out it is actually A squared plus B squared. Maybe a way of thinking about this, that's sort of like maybe the average value of the radius squared over 2, right? And I think there's a way of getting that to make sense, because this is maybe, I don't know if it's going to make my list that's on the slide here, but another example could be like a cylindrical shell. So the idea behind that one, this is one, it's not, I know this one's not going to be on the slide here in a second. And the reason why is this one is, from a certain point of view, perhaps trivial, because with a cylindrical shell, we're imagining like, it's kind of like the hollow cylinder, but it's really so hollow, or maybe the part that is not hollow, right? The outer shell is really, really thin, so thin that we're even ignoring it. In that sense, all the mass is kind of at a distance corresponding to the radius of this cylinder. In that sense, it's no different than from a rotational point of view. The amount of rotational inertia is no different from just a point mass at some fixed radial distance r from the center of rotation, which means this one, the formula would just be mr squared. So if you ask, like, why didn't I include that one? And I think that kind of, I'm writing it here because I see a connection between this and this one. Like if I said this hollow cylinder really is becoming so hollowed out that this is just a really super like eggshell thin shell out here, that means A is approximately equal to B, is maybe approximately equal to just what I called R over here. And if these are both R, I'd have R squared plus R squared is 2R squared, but then that would cancel that half there, and I just have MR squared, right? So that's maybe a way of seeing how this sort of is just like the average of the radius squared for this one. So anyways, kind of an interesting thing to discuss there. In this class, like I said, we're not really focusing on how to calculate these because pretty much all of these require calculus. I mean, in the last example, we saw how, we're really just summing up masses and summing up the MR squares for those masses. So that's something that I think we can understand. But, we're not going to do any integrals in this. And some of them actually get really, really hard. So I would say even if you have seen how to do that or did see how to do that, most people, including me, would rather just look these up or just know some of the common ones, because if you forget, it's really quite a chore to get to any of them, except maybe the really simple one like the cylindrical shell we just discussed. Anyways, let me put the answer up here. So it's probably not in the same order. Did I get it all correct? We got the sphere there at 2/5 mr squared. I guess I used lowercase m and lowercase r, and this is all uppercase for some reason in this table, probably because it looks better on the slide. We have the 1/2 mr squared for the cylinder. Those two, you can kind of, if you ask, like, what do those numbers really mean, right? What does a 2/5 versus the 1/2 really mean? The thing about a cylinder is if you look at the distribution of matter, more matter is at a larger radius or radial distance from the rotation axis than there is for a sphere, right? Because the sphere kind of, like, I guess the farther away from you get the rotation axis, it kind of narrows, is one way of thinking about it, right? And so that's why the sphere should have a smaller number there. So that's what that, you could maybe say that that's a geometric factor. It tells you how the distribution of matter as a function of kind of distance from rotation axis, how does that really affect the overall rotational inertia that this moment of inertia is quantifying. And I think, let's see, I think everything else, we got the 1/12 there for the center axis, 1/3 for the end axis, and the 1/2 m a squared plus b squared for the hollow cylinder.